तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will talk about the distribution of water. Now, a water distribution network consists of pipes with appurtenances, and it transports water from the treatment plant to the consumer's tap. It includes storage, balancing reservoirs and service reservoirs. Now, it is basically designed to adequately supply the amount of water for domestic purposes, commercial purposes, industrial purposes and firefighting purposes, and the adequacy of the design is checked by seeing whether we have enough pressure in the pipeline or not. Now, a good distribution system should supply water at consumer's tap with reasonable amount of pressure. It should meet the fire demand, it should maintain the water quality. Like when we supply water to the consumers from the treatment plant, we add chlorine at the treatment plant, but the residual chlorine at the tap level is more important for the health of the consumers. So, whether in between what is happening to the water quality is also very important. Now, water distribution networks should also not have many leaks, and then the water, the wastewater from the ground should not enter into the water distribution network. Now, we have to design a water distribution network such that the water quality is maintained very well. Now, a water distribution network should also be easy to operate and maintain. It should not be very difficult to operate these water distribution networks, and when we maintain these networks, it should not have it should not cause much of disruption to traffic. A good distribution system should also be reliable. What we mean by reliability is, let us say one or two pipes are breaking down in the system, and because of that breakage, some of the consumers may not be able to get water for long periods of time. That kind of a water distribution system, we say it is unreliable. So, the supply should be there even when some breakage is there in the system. So, it should be reliable. Now, as I have already mentioned, whenever there is a breakage to the water distribution network, and when we go in and repair that, it should not cause any disruption to the traffic. And one of the most important things in the design of water distribution networks is the initial cost, that is the capital cost. Then we also have the operation cost, particularly if you have a pump scheme, then we expend lot of power in operating these pumps, and that pumping cost and of course the maintenance cost. So, all these three costs, capital cost, the operating cost and the maintenance cost, that should be a minimal. Then we say that it is a very economical design. Then there are three types of distributions, water distribution systems. Three-type distribution system, combined, not three-type distribution system, it is a gravity system, then the pumping system and a gravity cum pumping or a combined system. Now, the choice of these systems depends upon the topography of the area. We will look at these systems in detail now. Like what you see here is a gravity system. Here the distribution reservoir, although I have not shown the treatment plant also could be very close to the distribution reservoir at a very high level, and your distribution area is at a lower level. Like here, this is the distribution area, this is at a lower level, and this distribution reservoir is at a higher level, and all the water flows through the distribution area by gravity. And when it flows by gravity in the distribution system, you have lot of energy loss. So, if you plot your energy grade line or the hydraulic grade line will be drooping. HF here shows what is the friction loss, and HE is the residual piezometric head at the tail end of the system, and this residual effective head should be more than what is desired. Now, what are the problems and what are the advantages of a gravity system? First of all, there may be some pumping required even in a gravity system, particularly if the source is at a lower level. You may have to pump water from the source to the either treatment plant, or if the treatment plant is also close to the source, from the treatment plant to the distribution reservoir. Now, this kind of a system is very reliable and it is very economical, because there is no operating cost here. There are no pumps and we are not expending any energy, and water flows only by gravity from the distribution reservoir to the distribution area. Next, we have a combined system. In a combined system, what we do is, there is a pump house which pumps water from the treatment plant to an elevated reservoir or a clear water reservoir which is at a slightly higher elevation. So, there is a pumping which is taking place from the treatment plant to the elevated reservoir, and from the elevated reservoir the water flows to the distribution area by a gravity. This is the most common kind of a system which we have in urban areas. In a pure pumping system, what we do is, it's meant for, we put a pumping plant and a treatment plant very close to the source. There may be a dual pumping necessary here. That's one stage of pumping from the source to the treatment plant, and another pumping from the treatment plant to the, directly into the distribution system. Here the water is pumped directly into the distribution system, and what you see here is a pump and pressure head, and then in the distribution system you will have the drooping energy grade line or the hydraulic grade line. Now, whatever is the elevation of the energy grade line or the hydraulic grade line at the tail end of this distribution area, that should be more than adequate. Now, the problem with pumping systems is, you are pumping water directly into the distribution system. So, if there is a power failure to the pumps, then the whole distribution comes to standstill. The consumers will not get their water. Another thing is, there is a variability in the demand. Always in a distribution system there is a variability in the demand, and that demand has to be met by variable operation of, or we have to choose the speed of the pump accordingly. So, we may need a variable speed pumps for that purpose. This is a disadvantage of a pumping system. Now, what are the design constraints? Whenever we are designing a water distribution network, there are certain constraints that our design has to meet. Our objective is, of course, to see that whatever we have designed, the capital cost plus operation cost plus maintenance cost should be a minimal. That is our design objective, but there are design constraints. Design constraints are basically to see whether our system is performing properly or not. Like at the ferrule level, a ferrule is the connection from the main system or your water distribution system to the individual buildings or individual houses. That is what we call a ferrule, and at a ferrule point you need to have certain amount of residual pressure. So, there is a constraint on that. If you are supplying water to a single story building, at the ferrule point you need to have a minimum of 7 meters of head. If it is a double story building, you should have a minimum of 12 meters, and if you have a triple story building, you should have a minimum of 17 meters of residual head at the ferrule point. At no time at the ferrule point the residual pressure head should not be more than 22 meters. We do not design for that. Let us say if you have a very high rise building and then you are supplying water through your system, then what you have to do is, you have to ask those people to have a sump or whatever, and then you supply water to the sump, not to the overhead tank of their building, because you cannot cross this 22 meters limit. And they can put a pump, and then from their sump they can take it to their overhead tank. Otherwise, if the pressure is not building up enough as you desire, then you may have to use a booster pump in such locations. Again, there is another constraint in terms of the flow velocities. You have a minimum flow velocity, that is to see that like there is no suspended matter which settles down. If the velocity in the pipeline is very low, then the suspended matter may settle down and the water pipelines may get choked. Not only that, if the velocity is not high, then the water quality also get deteriorated. So, you should not have any stagnant water in this distribution system. So, you need to maintain a minimum velocity of 0.6 meters per second. Similarly, there is a constraint on the maximum velocity. There is a constraint of maximum velocity is 2.3 meters per second. We cannot have any velocities anywhere in the system which is greater than 2.3 meters per second. This is because of the transients. If the transients get created in your systems, that is, if the velocity changes by 1 unit, then there is a corresponding change in the pressure which is going to be very high. So your initial velocities itself, you should not have very high velocities. So you need to have a maximum constraint on the velocity which is around 2.3 meters per second as per the Indian standards. Then in a water distribution system, you have two different types of operations. They are continuous systems and intermittent systems. In a continuous system, the water is available 24 hours a day. Now that is the one which all the consumers would love to have. If we have enough water to that we can supply, and if we can supply at the enough pressure, at the desired pressure. But then that kind of a system is going to be leading to lot of wastage of water. First of all, if the people know that the water is being supplied 24 hours a day, then they tend to waste water in the houses or in the buildings. Not only that, if we are supplying water 24 hours a day, and let's say there is some leakage in the pipeline. So if you are supplying 24 hours a day, then the amount of water that goes out of this particular leak will also be very high. So there is more wastage of water in a continuous system. But one advantage of a continuous system is you can easily maintain the water quality in the distribution system. We go for intermittent systems of operation, particularly when the pressure that you cannot supply water to all the localities in your municipality at the desired pressure, and sometimes enough quantity of water may not be available. Intermittent system means basically your water you are supplying only during fixed hours in a day. Now there are some problems with these intermittent systems. It's because your firefighting cannot be met adequately. Let's say you are not supplying water through your distribution system and then suddenly the fire breaks out. Now that time we cannot draw water from your distribution system. Then it also requires some amount of domestic storage, because you are supplying water only during few hours, but then you need water throughout the day. So at the domestic level you need the storage, and because it is operating for only few hours a day, the water quality cannot be maintained adequately in an intermittent system if you are not careful. Then another important thing is, in an intermittent system you may have to use greater sizes of pipes, because the whole day's quantity or the demand is met only during few hours of the day, or let's say 80% of the demand is met only 3 hours of the day. That means the discharge or the flow rate through all these pipes will be very high. So to carry that particular discharge, you need to have larger sizes of the pipes. So that may be very uneconomical. Again, in any water distribution network, we not only have the pipes, but we also have reservoirs. The reservoirs, there are two types of reservoirs. One is a storage reservoir and the other one is a distribution reservoir. In a storage reservoir, basically is meant to store the water, the filtered water that is coming from the pump, the treatment plant. Now we may operate the distribution network only for some few hours, but then you need to store the water for to meet the demand for a 24-hour a day. So that means the capacity of the storage tank, normally we take about 14 to 16 hours of daily average flow. Then we also have distribution reservoirs. The distribution reservoirs are meant to meet fluctuating demands. They also are meant for equalizing operating pressures. First of all, in any distribution network, the flow rates in the system are going to vary even on hourly basis, even on minute basis sometimes. So we have to be able to absorb these variations in the demand that is coming from the distribution system by putting a distribution reservoir. Again, this, if we don't have the distribution reservoirs, then we may have to have variable speed pumps. That means we cannot operate the pumps at a uniform speed. So if you don't have a variable speed of pumps, then it's going to have an effect on the pump life and then the pump efficiency. So what we do is, when we have a distribution reservoir, during some as the pump will be operating at a constant speed and we will be taking all that intake, but then the distribution system itself may not be requiring all this water that the pump is giving. So if the pumping rate is more than your demand, then the water will be stored in the distribution reservoir, and maybe at a later stage your pump may be operating at a maybe giving certain discharge, but your demand is very high. If the demand is higher than what is the pump discharge that is coming out, then you take that extra water from the distribution reservoir. So that way we can operate the pumps at a uniform speed. Now what happens with this is, it will actually reduce the sizes of your pipes, it will reduce the sizes of your pumps, it will also reduce the sizes of appurtenances and all those things. So because of this reduction in the sizes, it also can reduce the size of your treatment plant, and because of this reduction in size you can achieve economy. Distribution reservoirs can also store water for emergency purposes, and they in fact can be used to maintain almost approximately almost uniform pressure throughout your distribution system. This we will see later. Now there are types of reservoirs, two types of reservoirs, like surface reservoirs and elevated reservoirs. Now the surface reservoirs are typically made of masonry or concrete, but when you construct these surface reservoirs, you have to line them up so that there is no leakage from the surface reservoir. So appropriate liners should be used for this purpose. Again, the surface reservoirs we also have to compartmentalize. I mean, we divide the whole surface reservoir into several compartments, and these compartments, let's say I have two compartments. One compartment I can dry it up and then I can use it for maintenance, whereas the other compartment can be used for storing the water and supply it to the distribution system. The surface reservoirs, you have to locate it at a very high points of in that particular area, so that the water can go from the surface reservoir to the distribution area by gravity. We also have the elevated reservoirs. These elevated reservoirs is the one you normally see in any urban area, or what we call overhead tanks. These overhead tanks in the earlier days, they are made of steel. In fact, most of the railways, whenever they have these overhead tanks, you can see that when you travel in the train, they are all made of steel, all the older ones. But the current trend is to make these elevated reservoirs using concrete. Now if these elevated reservoirs can also come in different shapes and sizes, like rectangular shape can be used, circular shape can be used, and conical shape can be used, and so on and so forth. And most common type of an elevated reservoir is an INZE tank. Now the location of these distribution reservoirs depends upon the topography of the area and how well you want to maintain your pressures, how uniformly you want to maintain the pressures. They are typically located centrally, so that the any farthest point from that distribution reservoir is more or less, I mean, let's say I have a point here, this is of equal distance from this central this distribution reservoir, another point is here, this is also almost at the same distance from the distribution reservoir. That way the head loss here will be almost equivalent to the head loss here. So the pressure here and the pressure here may be maintained more or less same. So again, the distribution reservoirs, the central location basically is meant to reduce these frictional losses. The distribution reservoir capacity, that depends upon how much you want to equalize your pressures and the flow rates, and how much you want to how much of storage you want to provide for service during the breakdowns, and then how much of storage you want to provide for firefighting. Let's say breakdown reserve is typically taken as 25% of total storage if repairs last only for few hours. Let's say if the repairs are going to last for lot more hours, then you need to have much more storage for supplying water during the breakdown. A distribution reservoir capacity for equalizing, you see this figure here, this is what we call a mass curve analysis. In a mass curve analysis, the time of the day is plotted on the x-axis, and the accumulated flow in millions of liters is plotted on the y-axis. When I say accumulated flow, what I mean is cumulative flow. If you look at this curve here, this curve that I am showing, this one, and it is also denoted here as cumulative demand curve. As let us say you start the day at 0 hours, and as it proceeds you add up all the demand as the time progresses and you plot that cumulative demand curve. And if you are having 24 hours of pumping, let us say continuous pumping, if 24 hours of pumping, you need to meet this total demand which is at this point. This is the total demand of the day, that I have to meet by pumping uniformly for 24 hours. So, if I join this point and the point O here, that will give you the rate at which, that will give you the cumulative pumping. Now, if you look at this point here, that A and A prime, the A and A prime tells you at this particular point the pumping is much more than the total pumping up till this point is much more than the total demand that needed to be met during that time. So, the pumping rate is more than the what we needed in the distribution system. So, this extra water needs to be stored, and where will we store this? We will store this in distribution reservoir. So, this A prime, this how did I get this A? By basically drawing a tangent to my cumulative demand curve, and that line should be parallel to this cumulative pumping curve. The line, the tangent, this line here, the dotted line, that should be tangent to the demand curve, cumulative demand curve. At the same time, it should be parallel to the cumulative pumping curve, and I see what is the max, this intercept, what is this difference between this value and this value, and that is what is needed here. This A prime is what I need to store during those periods when my pumping rate is more than what is my demand. If you look at in this location here, here again I have a tangent, the BB prime, which is tangent to the cumulative demand curve. At the same time, it is also parallel to the cumulative pumping curve. Now, at this stage, what kind of a situation we have? My demand is more than my pumping rate. So, that means because my pumping rate is less than the demand, I have to meet that extra demand by depleting from the storage, and that's and that water I am going to get from my distribution reservoir. So, this particular intercept here, that BB prime, is what is required to take it out from my distribution reservoir. So, the total capacity of the distribution reservoir is then is equal to BB prime plus AA prime, or the distance between this BB prime, the tangent to the demand curve at this location, and the tangent to the demand curve at this location. This is how I will find out the capacity of the distribution reservoir. Now, the distribution reservoirs are also used for storing water for firefighting purposes. Now, supply of water for firefighting purposes is normally based upon how long the fire is going to last and under what kind of development, how many people are going to get affected by this particular fire. Typically, what we do is the amount of water that is required to fight a fire which is going to last for 10 hours and in an area where 6,000 people are living. You can also find out what is this capacity for firefighting that I have to include in my distribution reservoir using this equation. R is equal to F minus P into T, where R is reservoir storage in liters that I have to allocate for firefighting, and then F is equal to fire demand in liters per minute, and P is reserve for pumping capacity. Sometimes I can meet this fire demand by increasing the pump capacity itself rather than taking it from the distribution reservoir. That is why I have this F minus P. So, P is a reserve for pumping capacity and T is equal to duration of fire in minutes. The other important thing about the distribution systems is the layout. The layout of a distribution system is very, very important in ensuring reliable water supply and also for designing a very economical system. There are 4 typical layouts that we adopt for distribution systems layout, and the first one is a tree system or a dead end system. In a tree system, you have a main line which is coming from the treatment plant or a distribution reservoir, and then this main line branches off into several submains. There is one submain here, there is one submain here, there is one submain here, and from the submain we branch off into what we call branches. Like I have a branch here, I have a branch here, one branch, a branch here and a branch here, and from the branch it gets divided into what we call a service connection. In this tree system, the water always flows in one direction. Like here the water is flowing in this direction, the water is flowing in this direction, water is flowing in this direction, and I have dead ends at the end of the system. So that is why it is also called a dead end system. Let us see what are the advantages and disadvantages of a tree system. A tree system is very economical to design. That is because in a tree system you have the capacity of the pipes, or the size of the pipes keeps getting reduced as I go to the downstream side, because only the main will have to carry all the water and the end of the system they do not have to carry much water. So the sizes of the pipes gets reduced as I go in the downstream direction in a tree system. So it is very economical to design. Then it always leads to a simple layout. So you just follow the roads and then things like that, and then a very simple layout. Again, whenever I have a system like this, I need to have what we call cut-off valves or isolation valves. That means when I want to maintain this particular part of the system, I need to have a cut-off valve which will cut off that particular part from the main distribution line. So in a tree type system, I need to have, let us say, a figure that I have shown here. I need a cut-off valve here, 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 like that. So if you look at this configuration, the number of cut-off valves in a tree system will be very less. So that is another advantage. Other advantage, which is not an advantage in terms of layout or anything like that, but it is very simple to analyze. The disadvantages of a tree type system is you have pockets of, in the system there are some areas where water will be very stagnant. Now stagnant water can deteriorate the quality of water, so we should avoid that, and that is not possible. I mean, it is not as much possible to avoid this stagnation of water as it is for other types of the systems. Now because the stagnation pools are there, it will also accumulate some sediment. If there is some suspended matter and sediment is there, they also get accumulated. Now a large number of scour valves are required to scour this particular sediment out of the system, and so that way, although we are economizing in terms of not having many cut-off valves, we are going to spend more money in terms of having more scour valves. And if you look at the layout here, let us say this particular line here breaks. If the line here breaks, then this area and all the areas that I am showing here will be out, will not be getting the water. So that way you do not have much reliability of water supply in case of breakdowns if you go for a tree type of a system. And other disadvantage is discharge for firefighting could be less in the tail end areas if you go for a tree type of a system. The other type of a system is what we call a gridiron system. In the gridiron system, you have a main, and this main gets branched off into sub mains here, like there is a sub main here, a sub main here, a sub main here, and sub main gets branched off into a branch line, and you have all these, so many of these cut-off valves to isolate any of the pipe for maintenance purposes, or when there is a repair is required, and so on and so forth. If you look at in a gridiron system as compared to a tree system, let us say I have this area. If this area, the water can come along this route, or along this route, or along this route. So even if one of the pipeline breaks or two of the pipeline breaks, I still will be able to supply water to a particular area. So the reliability is already built into the system. Reliability in case in terms of be able to supply water during the breakdowns. Not only that, the pressures also will be able to, you will be able to maintain the pressures also in a much better fashion as compared to a tree type of system. This is the advantage of a gridiron system. Okay, and there are no stagnation points in a gridiron system, and because of that the scour valves, the number of scour valves will be less, and as I already mentioned, there is more reliable water supply. Then the disadvantage is large number of cutoff valves, but I do not think that is really a disadvantage in terms, I mean maybe for a very very large system the number of cutoff valves will be very high and things like that, but one should not worry about that. Then the other main disadvantage of a grid iron system, if you look at the figure, you compare the grid iron system I am showing here with the tree type of system that I am showing now. Between these two systems, which one will have a longer lengths of the pipes? It is obvious that grid iron system will have longer lengths of the pipes, and not only that, it also will have larger diameter pipes. Let us say for example, a demand here is being met through this pipeline as well as this pipeline, or maybe this pipeline and this pipeline. The demand here is being shared by several pipelines. So this pipeline which is supplying the demand here as well as which is catering to the demand here also, because of that it may have to carry more amount of water. So the size of the pipeline also will be larger. I mean typically the sizes of the pipelines will be larger in a grid iron system compared to a tree type of system. Third type of a layout is your ring system. The advantages and disadvantages of a ring system compared to a tree type system are exactly similar to what we have for a grid iron system, except there is only a difference in terms of the layout. Here I have a main which branches off into two mains like in a circular fashion and then joins here and again it goes off, and within this particular ring I will have my submains, branches and service connections. Like there is a submain here and there is a submain here, there is a submain here, there is a submain here. So this is what we call a ring system. With the ring system what happens is, because this main line is going to be a larger diameter pipeline, the pressure drop from here to here will be much less. You know that the pressure drop is inversely proportional to the fifth power of diameter. So if the diameter is large, then the pressure drop will be less. So lengths of the mains are very long in the ring system, as you can see in this particular figure. The last type of a system I want to show you is the radial system. In the radial system, the main will come here and then it will be connected to the 4 distribution reservoirs that I am showing here. There is a distribution reservoir here, there is a distribution reservoir here, there is a distribution reservoir here, and there is a distribution reservoir here. So this main will be primarily supplying water to the distribution reservoirs, and from each distribution reservoir the water will be flowing along the radial, the pipes laid out in a radial fashion in that particular area where you are supplying the water. Like this here I am shown. Similarly this one will supply to this particular area. So this way also will be, because these distribution reservoirs can be an elevated reservoir, I will be able to maintain the pressures much more uniformly in a radial system. Now what are the design steps that I have to take for designing a water distribution network? This is very very important. First thing you need to do for designing a water distribution network is you have to conduct surveys. Now after conducting the surveys like topographical survey and geographical survey and the survey for laying out the street lines and then like roads and then other whatever the utilities that you may have like electrical lines, how they are going and all those things, for all that you need to conduct surveys. So you conduct the surveys. After conducting the survey, you come and then fix the alignment of rising main. Let us say you have a distribution reservoir or a storage reservoir, then you have a rising main from your treatment plant to that particular reservoir. So you fix the alignment for the rising main. So you locate the reservoir, you locate the reservoirs depending upon the topography. For that you need a topographical map of the area. So you have to have a topographical map of the area also, and then you also have to have a detailed map of the town which is showing all the roads, then other utilities that are going along the roadside like drainage pipelines, electrical conduits and so on and so forth. Now those things are again should be shown according to the cross sections of the streets, etc., where exactly these lines are there. Now after getting all this information, in fact the current practice is you can use a geographical information system, GIS package or whatever, for collating all this information into a GIS information system. Okay. Then the next thing is you make a tentative layout, mark a tentative layout of the pipeline. Then after marking the tentative layout of the pipeline, depending upon to which area you want to supply the water, you show the positions of the reservoirs, valves and other appurtenances. From the maps and the way the pipelines are laid and the areas to which these pipelines are supplying the water, go to those areas, conduct the population survey or the census survey, or from the census data you will be able to get what is the population that is being served by each pipeline. Now if you know what is the population that is being served, and then you also know how much water you have to supply depending upon the demand, let us say 100 LPCD or 150 LPCD and so on and so forth, you will be able to find out what would be the carrying capacity or what should be the carrying capacity of each of these pipelines, or what should be the demand at each of the nodes in the network. That you can get, as I said, from the population density and the area that you have. Then what you need to do is you need to assume appropriate diameters for these pipelines. After that you have to analyze the system. At this stage what do we have? We have the network, we have the connectivity of these pipelines, and we also have their lengths, the diameters. We would have chosen the material for the pipeline like asbestos cement pipelines or what concrete pipelines or galvanized iron pipelines or plastic pipelines or whatever, depending upon the material you know what is the resistance to the flow of these particular pipelines. All this data we have, we can check for the pressures in the system at different locations by analyzing the system. Then after checking for the pressures, when you are checking for the pressures or when you are analyzing the distribution system, you will also be getting what is the flow rate in each of these pipelines. Then check for the whether the assumed diameters or the assumed system is able to meet all the constraints. I have already mentioned to you what are the constraints. Let us say the pressure at any ferrule point should be greater than 7 meters if it is serving a single story building, or the velocity should be greater than 0.6 meters per second, or the velocity should be less than 2.3 meters per second, and so on and so forth. So you check whether these constraints are being met or not. Once these constraints are met, that means you have chosen a plausible system which can serve your purpose. But then you do not stop at this stage. You assume another set of diameters. Once you assume another set of diameters, you go and then do this analysis all over again and see whether it is meeting your constraints or not. Let us say this is not meeting your constraints. That means this particular set of diameters are what we call the decision variables in our design that should be thrown out. You choose another set of diameters and then do the analysis. Now after doing this, you repeat this procedure for several of these alternative diameters, the set of diameters that you have chosen, and let us say you have chosen some 20 of them, and out of 20, 12 are meeting your constraints and 8 are not meeting your constraints. You throw these 8 alternatives out which are not meeting the constraints. You choose the other 12. Out of this other 12, you see which one is giving you the least cost, because you know the lengths and you know the diameters, you know the material, you will be able to find out what is the cost of your system in terms of the capital cost. You also see if it is a gravity system, then you will not have much of operating costs coming into the picture. So you take this capital cost and see out of these 12 design alternatives that you have given, which is giving you the minimum, the cost, and you choose that one. Now if you do this and if you take a very large system, let us say you have 500 nodes and then 600 pipelines. Now how many alternatives that you can do and what is the amount of time that is going to take for analyzing this? For these purposes you cannot do hand calculations and you have to use the software packages, and many of these software packages are readily available these days. Like for example, you can use what we call KY Pipe. This is a software package developed by the Kentucky University that you can use. This is commercially available in the market, and there is 2 levels of doing this. One is the simulations, or what we call the analysis of the system. Now if you can do this analysis, but then when I say you choose 12 alternatives or 20 alternatives, where do I stop? Do I stop at 100 alternatives or do I go for 600 alternatives? Because let us say if I have 600 pipes and then each pipe can take 4 or 5 different values of the diameters, the commercially available diameters, then you see how many alternatives that you can have. So that kind of a design, what is the least cost, the design that gives you the least cost cannot be done by hand calculations. So you need to have what we call optimization subroutines for doing this. So there are methods which are available for doing this, and that is beyond the level of this particular course, and you can learn that in an advanced course on how to do the optimal design of a water distribution network. In the water distribution network analysis, okay, before I go to this water distribution network analysis, I want to tell you one more thing. Here I talked only about the diameters. Like I said, select the system that satisfies all the constraints and is most economical. Here I have not talked about the design of the layout itself. There could be at the outer level, there could be many layouts which are possible, which can supply the water and which is reliable. Then which layout would you choose? So that is the outer loop in your design procedure. Let us say first you choose a particular layout, and for that particular layout you choose what are the most economical diameters that you can get. Then you change the layout, and again for the second layout, the second alternative layout, again you choose what are the optimal diameters that are possible. Like this you can have an outer loop for designing the layout itself. While doing that layout design, you also have to talk to field engineers to see what kind of a field constraints that may come in. You may go in and give a particular route, but then the field engineer will go in and say that it is not possible for me to acquire land for laying this pipeline, or if I try to lay this pipeline, these are the problems I am going to have, like that. So you have to incorporate those kind of constraints also while doing the design of the water distribution networks. Now let us talk about this distribution network analysis. What is this distribution network analysis? What is the definition of the problem? I give here a very simple problem. I have a network of 5 pipes and I have nodes 1, 2, 3 and 4. When I say the demand here, that means from the node 4 there will be a system that is going in, a local level system which is going to draw water from this major system to meet the demand here. So if this node 4 is catering to certain number of people, depending upon that population and what is the supply rate, let us say 100 LPCD or 150 liters per capita per day or whatever, I will be able to find out what is the demand. So in the network here, I have already given you what is the configuration of the thing. I have given you the layout, and I will give you what is the demand here, what is the demand here, and what is the demand here, and this particular network is being served by a distribution reservoir here. So I will also tell you what is the water level in the distribution reservoir. So given the water level in the distribution reservoir, the demands and the pipelines and the lengths of the pipelines and the diameters of the pipelines, the question is what would be the piezometric head at node 3, node 4 and node 2, and what is the flow rate in pipe 4, pipe 3, pipe 1, pipe 2, etc. That means I have to find out the discharges in all the pipes and the pressures or the piezometric heads at all the nodes. Please note, the piezometric head at node 1 is known because this node 1 is connected to a distribution reservoir. If I know what is the water level in the distribution reservoir, then I would know what is the piezometric head. So piezometric head at 1 is known, but 2, 3 and 4 is what I am trying to find out. So once I do this analysis, then I will be able to go and then see whether the pressure here at node 2 is more than what I require, and whether the velocity in pipe 3 is more than 0.6 meters per second or less than 2.3 meters per second, etc. So that way this analysis is very important. This analysis is based on 3 principles, 3 basic principles. One is flow into a node is equal to flow out of a node. Like if you take node 2, the flow rate, let us say, is coming into node through pipe 1. So flow rate at pipe 1 should be equal to, let us say the flow is going out of the node 2 through us the node 3. So that is flow out, and similarly flow is going from 2 to 4. So that is also an outflow. So Q1, the discharge in 1 should be equal to discharge in 3 and plus discharge in 4 plus the demand. So the flow in should be equal to flow out. That is one principle. Then piezometric head at any node is same irrespective of path we take for computation. That means let us say I have node 4, I know the piezometric head at 1, piezometric head at 3 is equal to piezometric head at 1 minus the loss in pipe 2, then loss in pipe 5 will give me piezometric head at 4. Similarly, the piezometric head at 4 can also be determined through the other route, that is piezometric head at 1 minus loss in pipe 1 minus loss in pipe 4 is equal to piezometric head at 4. So irrespective of which path I take this path or I can go like this path, whichever the path I take, the piezometric head at 4 should be same. That is the second principle. Then the third principle is the head loss in any particular pipeline is equal to RQ square, where Q is the flow rate, HU is the piezometric head at the upstream end, and HD is the piezometric head at the downstream end, R is the resistance factor. If I am using Darcy-Weisbach equation for calculating the head loss, then R is equal to FL by 2G pi by 4 square d to the power of 5, where D is the diameter of the pipeline and L is the length of the pipeline and F is the Darcy-Weisbach friction factor. I can also use other equations for finding out this resistance. Now what are the methods of analysis in terms of the formulation? These three principles can be used to formulate the problem. So the formulation could be, as I mentioned, node balance method, or it could be a loop balance method. Then this formulation means I will formulate a set of mathematical equations which describe the flow process in this network, that is the formulation. Then once I get this set of mathematical equations, then I should have how to solve these mathematical equations. Then there are several ways of solving these mathematical equations. As you see little later, this set of mathematical equations will be a set of non-linear algebraic equations. So I have to have a method for simultaneously solving this set of non-linear algebraic equations, and that can be done through two methods. That is what I call the solution, either Picard iteration method or Newton-Raphson method. In this particular lecture, we only talk about the formulation. Now referring to the figure, what we know are demand at each node is known, R for each pipe is known because I know the length, I know the diameter and I know the material of the pipe. So I know the resistance factor for each pipe, and I also know the piezometric head at node 1 because the piezometric head at node 1 is related to what is the water level in the reservoir. So H1 is also known. What are the unknowns? I need to know what is the flow rate in each pipe, that is Q, and piezometric heads H2, H3 and H4. You look at this figure, H2, H3 and H4 I need to find out, Q1, Q2, Q3, Q4 and Q5 also I need to find out. Now how do I formulate this? There are 8 unknowns and we require 8 equations. In fact, as I go through this, I will show you how to reduce this number of equations. We may not require all the 8 equations. We first write a flow balance equation at node 2. When I write the flow balance equation at node 2, looking at the figure, I can say that Q1, that is the inflow, minus Q3, that is the outflow at node 2, minus Q4, that is outflow at node 2 towards node 4, and the demand at node 2, that is DE2. They should balance out, and Q1, to get the flow rate Q1, here it depends upon head at 1 and head at 2. So Q1 can be written in terms of H1 minus H2 divided by R1 square root. Again, the Q1 depends upon head at 1 and head at 2. So Q1 or Q1 square will be H1 minus H2. So Q1 is equal to H1 minus H2 by square R1 square root. Isn't it? Now in the WDN analysis, I get this equation for the flow balance at any node like H1 minus H2 by R1 square root, H2 minus H3 by R3 square root, H2 minus H4 by R4 square root minus DE2 is equal to 0. That is the nodal balance equation at node 2. Similarly, I can write nodal balance equations at other node 3 and node 4. Now, I have 3 equations. In these 3 equations, R1, R3 and R4, DE2, DE3, DE4, R3, R4 here, all these things are known, and H1 is also known, and the only unknowns are H2, H3 and H4. So, I have 3 equations and I have 3 unknowns. So, these 3 equations and 3 unknowns can be solved for simultaneously. So, depending upon the number of nodes I have and depending upon the number of reservoirs I have, that means the number of reservoirs I have means I know the reservoir water level. So, if I know the reservoir water level, the node connected to that reservoir will know what is the head at that node. So, the number of equations then depends upon the number of nodes I have in the system minus whatever the number of reservoirs I have. Let us say in this particular case I have 4 nodes and 1 reservoir. So, the number of equations that come is 3 equations in 3 unknowns, and these 3 equations can be solved for H2, H3 and H4. Once I solve for H2, H3 and H4, I go back to my resistance equation. So, in any pipeline, I know the flow rate is proportional to what is the head at the upstream node and what is the head at the downstream node. So, I know for any particular pipe, I know what is the upstream node and what is the downstream node. If I know what is the upstream node and what is the downstream node, I will be able to find out what is the flow rate in that particular pipe, because I know what is the length and what is the diameter. So, this is what I will use for basically analyzing the network. Now, this I have already told you that I have 3 equations and I use for a appropriate numerical method. As you can see, these equations here are non-linear equations. They are algebraic, but they are non-linear equations. Now, when you want to solve this system of non-linear equations, there are many numerical methods which are possible. One is the trial and error method. I will assume what is H2 and what is H3 and try to get what is H4 here, and I will substitute what is H4 here and assumed value of H3 here and get a better value of H2, and I can keep doing this trial and error procedure or an iterative procedure. Once I do this, eventually as the iterations proceed, I may have a stable values of this H2, H3 and H4, and I say that the system has converged. This is an iterative, what we call numerical method. However, one has to be very careful while solving these equations by these numerical methods. You may start with some assumed values of these unknowns H2, H3 and H4. Then as your iterations proceed, you may never be converging to certain definite values of H2 and H3 or the correct values of H2 and H3 and H4. In that case, we say that numerical method is diverging. So, you have to choose a proper numerical method for solving these equations, this system of equations, and several methods for these things. As I mentioned, we have the Picard iteration method and Newton-Raphson iteration method. Now, Picard iteration method is lot more stable than Newton-Raphson method, but that also one cannot say. Some methods which are very stable for certain systems may not be very stable for other systems. So, that is why people keep working very much into finding out more and more numerical methods for solving these equations. Anyway, we can solve this system of equations by any of these methods, and then we can get the solution. Now, in the way we formulated here, that can be extended if valves are present or if pumps are present, and it is also not very difficult to put all these things in a computer code. I have already told you about a computer code developed by University of Kentucky called KY Pipe, but you also have the computer codes developed by other agencies like EPA-NET, that is developed by United States Environmental Protection Agency. This particular program is available on the internet, and one can easily download this particular thing from the internet, and one can use it for solution purposes. In fact, you can do it yourself. You can download it from the internet, and it is very easy. Then you will see how the input should be given and how the analysis, then the network, the program will make the analysis and will give you the results. This EPA-NET will also actually track the chlorine concentration in a network. If you give what is the chlorine concentration or what is the chlorine dosage at the treatment plant, it will also tell what will be the chlorine concentration at different points in the network, and you can compare that with whatever the standards you may have and see whether the water quality is maintained properly or not. In this particular lecture, I just want to summarize. I gave an overview of what is a water distribution network and what are the different criteria or the constraints that a good design should meet. I talked about what are the different layouts for water distribution networks, and we also discussed about the distribution reservoirs, how to find out what is the capacity of a distribution reservoir. We looked at different layouts for the water distribution networks, then we looked at the design steps, what are the steps we should take, follow for designing these networks, and how to analyze a given distribution network. Let us say somebody comes in and gives you that, like, these are the lengths, these are the diameters, this is the network, can you tell me what are the pressures at different locations, what are the flow rates, can you analyze this network and then tell me whether it is meeting all my constraints or not. You will be able to do through water distribution network analysis. That also we have seen, and I mentioned about Newton-Raphson method. I have also mentioned about other numerical methods like Picard method. I leave it as an exercise. Basically, you can go in and read a little bit more about these things, and in the next lecture probably we will go in and look at aspects of drainage network design.